Hi everyone. In the previous lesson, we were talking about continuous compounding, and we brought up inflation as an example. But what I want to talk to you about today is that the model for exponential growth absolutely does not only have to apply to money. In fact, there are many more applications of it outside of the world of finance than inside it. So the lesson for today is about exponential growth and decay. And really, it doesn't do anything different. It's exactly the same model as continuous compounding. So I'm actually going to write that. The behavior and the model for exponential growth and decay. And yes, I'm talking about decay 2 now. Growth and decay in nature is just like or just the same as continuous compounding. There's a little bit more notation, or maybe I should say the notation is a little bit different. So I'm going to introduce it for you right now. So notation. A of t. So we will call this the amount of whatever it is at time t. T is generally not going to be always years. You'll see what t is dictated by. A lot of time t will be years, but you'll notice in some examples that t can even be minutes or days or hours. So we are less bound by the whole idea of time being years when we're talking about exponential growth and decay than we were when we were talking about money. A sub 0, that's the initial amount. And K is the relative rate, and I'm going to write here, of growth or decay. Okay, so your book, so if you're watching a lot of videos that come with your book splits this up, and I actually don't like that they do, because they treat it as two completely separate and two completely different scenarios when you're looking at growth or decay, but there's really no difference mathematically. If K is positive, we are seeing growth. If K is negative, we are seeing decay. Okay, so I don't go through the whole process of, well, if it's decay, then it looks like this. If it's growth, then it looks like this. Okay, so in the context of growth, one really important time that is sometimes either given to you or you are asked for it is doubling time. Okay. So doubling time is exactly what it sounds like. It is the time for a population or a size of a thing. You'll notice a lot of the time it's a population to double. Okay, so this might be the size of a bacteria culture. Honestly, this might even be the size of a population infected with a given virus. So, for instance, in the midst of the beginnings of the coronavirus pandemic, one of the things that was talked about a lot is the doubling time. How quickly is the number of people who are infected with the virus doubling? And we saw that before containment efforts, it was something like every 2 days, right? So let's kind of think about how that works. So say that we have a relative growth rate K, okay, and let's say that the doubling time is D, okay? We'll call it D for now. It actually doesn't matter what we call it. So the initial amount is A0. I don't really care what it is. D time later, the initial amount has doubled. So it's grown to 2 times A0. Okay. So what is the rate of growth if that is my doubling time? So let's solve this. This is an exponential equation. Exponential equation. And let's solve it for k. So you can see very quickly, and I kind of hope that this reminds you of the conversations that we had with the money problems, because you can see very quickly it doesn't matter what the initial size of the population is, because the very first thing we do is we divide both sides by A0. So we end up with 2 is equal to e to the power kd. So taking the natural log of both sides. Oops. Right, so you remember by properties of logarithms, when you have a power inside a log, it hops out to the front. So we have the natural log of 2 is equal to kd times the natural log of e. And of course, this is 1, right? We've talked about that before. And since we are solving for k, at this point, we'll divide both sides by d. So the natural log of 2 divided by whatever the doubling time is, that's your growth constant, k. Okay? Notice that the natural log of 2 is a positive number. And so this population is growing because the doubling time, obviously time is positive, the log 2 is positive, so the quotient is positive. So I'm actually going to write that here sort of in purple. Note that k is greater than 0. An analogous question in the conversation about decay is the one about half-life. So in the decay conversation, when you're looking at something that's decaying, you're looking at half-life. So one really common place where you might encounter conversations about half-life is in the pharmaceutical industry, right? So when you ingest a substance, whether it's Tylenol or a more potent drug of some kind, your body starts metabolizing it, and the compound itself might be stable or it might be unstable. So the half-life is how long it takes for the amount to have shrunk to half of its original size. So time for the amount or the size to shrink to half its initial size. So half-life is actually a really interesting concept because, and we'll be talking about it at length in an example lesson that I'm going to do later, because one half-life later, you're down to half your original size, but 2 half-lives later, well, you're down to half of your original size, right? So 2 half-lives later, you're down to 1/4 of your original size. 3 half-lives later, you're down to 1/8. So that's something we're actually going to explore a little bit in a future lesson. Okay, so let's call capital H our half-life. And same thing, what does it mean to be looking at half-life? It means that your present amount is half of your initial amount. So again, the time that's elapsed is h, our half-life. So let's, same thing, we're going to do exactly the same thing as we did in the previous example. This is an exponential equation. And we're going to solve it for k. Okay. So same thing, right? I really hope that by now this has almost become internalized. We're going to divide both sides by a0. So we have 1/2 is equal to e to the power kh. Again, we'll take the natural log of both sides. Again, by properties of logarithms, the kh simply pops out to the front. So we end up with the natural log of 1/2 is equal to kh times the natural log of e. And again, we've said this before, the natural log of e is 1. So since that's 1, all we need to get k by itself is divide both sides by h. So we get the natural log of 1/2 over h. And that's our k. So I want to once again note that the natural log of 1/2 is a negative number. Feel free to check that for yourselves. And we see that in this case, the k is negative. So if you are ever in a situation where you are given the doubling time, or in the case of a decaying population or culture, you're given a half-life, you immediately know what the decay constant in the case of half-life or the growth constant in the case of doubling is. So you can still solve for k, but you know ahead of time what it is. The last thing I want to say in this video is this. I'm going to use this little corner over here to do it. If doubling time is known, and you'll see that in a lot of problems you're given the doubling time. Well, watch. The amount at time t is a0 e to the power kt. Okay. And we just found out that k is the natural log of 2 over d. So this is the natural log of 2 over d times t. And now we're going to use a little bit of properties of exponents. You know that if you have two exponents being multiplied, you can split that up into something that's raised to a power and then to another power. So I'm going to write this as e to the power natural log of 2 to the power t over d. And because exponents and logarithms are inverses of one another, raising e to the power log 2 is just 2. So in fact, you can rewrite the function that models this growth as a sub 0 times 2 to the power t over d. So if you are given doubling time, you can either express the growth as base e, or you can express the growth as base 2. In your homework, you'll have a couple problems where you're asked to find both the base e and the base 2 function. And when you're solving problems, you'll notice that the base 2 one is a little bit cleaner. There's just less clutter. So a lot of you will favor this version of the function in the situation where doubling time is known. By that exact same token, if half-life is known, well, check it out. Same exact thing. A of t is a0 e to the power kt. Okay. except k is the natural log of a half over h. We found that over on the half-life side. So we have e to the power natural log of 1/2 over h, where h is our half-life, times t. And you'll notice I'm going to do exactly the same thing as I did in the previous problem, or the previous example here. And then we have the e to the power natural log of 1/2 to the power t over h. And again, because exponentials and logarithms are inverses of one another, they undo each other. So this becomes a sub 0 times 1/2 to the power t over h. And so again, in your homework, you will have problems where you're given the half-life and you can express the decay of the population as a function base e, or you can express it as a function base 1/2. And what a lot of you will probably notice is that the base 1/2 function is just easier to work with. So again, this is in the situation where the doubling time d is known, and this is in the decaying situation where the half-life h is known. So this is just a little bit of an overview. The main thing I want you to get out of this video is the idea that for exponential growth and decay that's occurring in nature, the model is exactly the same as the model that we had for continuously compounding interest, and that with growth and decay there are these two interesting ideas. The idea of doubling time, how long it takes for a population to double, or the half-life, if something is decaying, how long it takes for something to get down to half of its original size. Okay, in the next lesson we'll look at a bunch of examples of exponential growth and decay, so stay tuned. I'll see you soon.